Hello, exercise on probability. Now suppose you have two dice and you throw the dice independently. One result has nothing to do with the other, informally speaking. Imagine the outcomes are independent. X is the sum of the dice. So it's the result of the first die, x1, plus the result of the second, x2. Okay? Y is the first minus the second, so x1 minus x2. And the exercise asks you, what's the probability that the sum is 9? That's the first part of the exercise. And the second part is the probability that the difference is 2. Okay, the first minus the second is 2. To do these exercises, this type of exercise, you have to understand first what you need to do first. You have to understand what's your sample space. Okay, that's the basic, most important thing. You have to list all your sample space to visualize mathematically in your mind somehow. Okay, here I draw all the possible outcomes. So for instance, this here, 4, 2, means the first die was 4, the second outcome, the second die was 2, and so on and so forth. Okay, both die getting 6, both getting 3 here, the first is 3, the second die is 5, all the outcomes. Then I ask you, what is the probability of each one of these outcomes? First, how many outcomes do I have? Well, we have listed things in 6 rows and 6 columns. So overall, 6 times 6, 36 possible outcomes, right? So my sample space here, omega, has 36 points. Okay, I can obtain 36 different outcomes by throwing the two dice. Okay, so my sample space has 36 points exactly. And what's the probability of a particular outcome? The first die having I and the second being j, where I and j are numbers from 1 to 6, integer numbers from 1 to 6. Well, if they are honest, all outcomes are equally likely. Each one of these outcomes is equally likely. I have 36 of them. I know that if I add up all these probabilities of each one individually, I get to 1. So tell me, 36 numbers, they are all equal to each other and they add up to 36, to 1. The number has to be 1 over 36. Okay? So the probability of each point here of my sample space is 1 over 36. Okay? So my sample space is just the list. 1, 2, 3, 4, 5, 6. Cartesian with itself. 1, 2, 3, 4, 5, 6. Cartesian product, the set of pairs where the first number in the pair is a number between 1 and 6, and the second is also a number between 1 and 6 integer numbers. Okay? And this Cartesian product has 36 elements. Now it's easy. To solve the problem, I have to count here. I know there's 36 possibilities, and I will count how many possibilities are satisfying my requirement that the sum is equal to 9. What are the pairs here that add up to 9? So in the first row here, the first number is 1. Is there any outcome that adds up to 9? No. The most that I get in the second die is 6, and this add up to 7, not to 9, not enough. How about here? The second row. No, here's not enough. That's 8. That's even smaller. 3, I can get 3 and 6. Yes, so this outcome adds up to 9. In this row here, I have this. In this row here, I have this, and in this row here I have that. So all in all, I have 1, 2, 3, 4 possibilities. So that's my solution. Or if I simplify this, it's 1/9. Okay? So that's probability that the sum is equal to 9 is 1/9. What is now the chance, the probability that the difference of the first minus the second equals to 2? Again, I have 36 possibilities, and I will count how many of these possibilities have this property here. Let me do that in red. So I want the first minus the second equals to 2. Okay? I want this to be equal to 2. That means that the first number has to be the second plus 2. So the minimum the second number is 1. So x1 has to be at least 3. So when I have 3 and I can have 1, that satisfies my property. Okay? How about this difference is 1, this difference is 0, this minus this, the difference is negative, doesn't work. How about in this row here? If my first number is 4, my second number has to be 2. And you can check those are the possibilities, right? Again, I have 4 possibilities, 1/9. And I can, with this technique, I can solve much more complicated problems even, okay? I can, for instance, you throw 3 dice, and what is the probability that their sum, it's gonna be 7. You do the list. You have 6 to the power 3 possibilities for your sample space, and then you count how many satisfy your requirement, okay? So, exercise. Now we have 3 honest dice. We throw the dice and we add up the results, right? And the exercise is asking, when you throw these 3 honest dice, what is the probability that their sum, it's gonna be exactly 8? Okay, so how can we solve this? So suppose the third dice, the result was 1. What has to happen to the other 2? Well, first things first. What's the sample space? I always tell, let's calculate the sample space. Now the sample space here, it's going to be the set of triples, where the first number is 1, 2, 3, 4, 5, 6, the second is any, and the third is any. So that's the set of I, J, K, such that I, J, and K belongs to 1, 2, 3, 4, 5, 6. Okay? So triples. The I is the outcome of the first, J the second dice, and K the third. Either one of them can be any number from 1 to 6, integer numbers. So we have how many elements in this sample space? We have 6 to the power 3. Okay? So 36 times 6, 216 perhaps. 6 times 6, 36, 18 plus 3, yeah. So now let's look here. If the third dice has 1, the other 2 should be all, the sum of the 3 should be 8. If 1 is 1, the other 2 have to be 7. Okay? If the third die is 2, the sum of the other two has to be 6. If the third is 3, the sum has to be 5, and so on and so forth. Okay? Now, how many outcomes I have here in this, how many possibilities here when the third is 1 and the other two add up to 7? So here I have 2 die and I have two numbers, pairs, and I have to add up to 7. So that will be here, 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 and here. All in all, I have 6 possibilities. Okay, so here I have 6 possibilities. Now the next one, x3 is 2, so x1 and x2 adding up have to find 6. What are the possibilities of having 2 dice adding 6? Well, it's here, 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 and here. 1, 2, 3, 4, 5. I have 5 possibilities in this case. Now, what's the when the x1 and x2 add up to 5? So I'm here, 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 and here. 1, 2, 3, 4 possibilities. x1 plus x2 equals to 4. How can I get to 4? Here, here, and here. 3 possibilities. And I think you know here I have 2 possibilities of adding up to 3, I'm sorry, here and here. And finally, if they have to add up to 2, I have only 1 possibility, this one here. Okay, so all in all, I have 1, 3, 6, 10, 15, 21. So all in all, I have 21 possibilities over 216. Okay, is this divisible by 3? I think so. And that is going to be a 82 perhaps, right? No. What's 216 divided by 3? 72. So that's the solution for this problem. 7, the probability that they add up to 8 is 7 over 72. Okay? There's another way of solving this problem, which is the following. You start the same, counting the 216 elements of your denominator of your sample space, right? But to compute this 21 here, let's be a little bit clever and let's look at what we want. We want how many possibilities we want for the equation x1 plus x2 plus x3 equals 8, where these xk's are numbers between 1 and 6, integer numbers between 1 and 6, right? It's the outcome of the die, the kth die throw of the die, okay? Let's do one magical substitution, mathematics after all. Let's yk be xk minus 1. So you have to have 8 things choosing x1 of the first type, x2 of the second, x3, and it has to be 8. Well, give 1 to each one, and since you have to add up to 8 and you already put 1 on each xk, the y's can start from 0 to 5. Okay, and the y1 plus y2 plus y3 equals 5, but now these y's, they can start with 0. They could be 0. Okay? How many solutions do I have for this equation y1 plus y2 plus y3 equals 5 when each variable y1, y2, and y3 has to be a number between 0 and 5, integer number? Right? Let's use the idea of anagrams. Okay? So first of all, I will give an example of a solution to this equation. The solution will be 1, 3, and 3. y1 equals 1, y2 equals 3, and y3 equals 1. These numbers, 1 plus 3 plus 1, they add up to 5. Good. And they are integer numbers. They are all numbers, valid numbers. Here I put these 5 objects as balls. I drew 5 balls. I draw 5 balls here. 1, 2, 3, 4, 5. And how I'm going to split into the first category, the second category, and the third category. Category means the value of y1, y2, and y3. I will put a separator, this red eye here. Okay? So in this case, for this particular example, there are lots of examples, of course, but for this example, on the left of my first separator, I have 1. Between the first separator and the second, I have 3 balls. And to the right of this separator, I have 1 ball. Another example, to the left, here I have 0 balls. Between the first and the second separator, I have 1, 2, 3, 4 balls. To the right of this, I have just 1. So that corresponds to this solution. Another example could be something like this. To the left of my left separator, I have 5. Between them, I have 0. And to the right of that, I have 0 balls. Okay? So all of these are solutions, and many other solutions would be valid. I'm just explaining how you map each solution of this equation with an anagram of a word which has exactly 7 letters, 5 O's, and 2 I's. The red are letter I's, and the balls are the letter O. So it's O, I, O, 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 I, O. Here, I, O, 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 I, O, and so on and so forth, okay? So each solution matches each anagram. And how do we count anagrams with repetition? Anagrams with repetition. So we have a word with 7 letters being 5 letter O's and 2 letter I's. That's how many anagrams we have. Okay? So 7 factorial is 7, cancels with the 5 factorial. I'm left with 7 times 6 and the 2 factorial in the denominator. 6 cancels with 2, I have a 3, and I have 21. Okay? So I have 21 solutions to this equation in y. So I have 21 solutions for the equation in x. And therefore, I have this 21 here in the numerator. Okay? For this problem is complicated, but this technique allows us to solve harder problems where just counting could be very tedious. It could take hugely impossible amounts of time. Okay? See you next time. Bye-bye.